Hello friends, today we are going to discuss exercise 12.1 in HK Das from the third question onwards. So the third question is, obtain the differential equation of which y square is equal to 4a into x minus a is a solution. So this is our first equation. Differentiate this equation with respect to x, we will get equation number 2. 2y dy by dx is equal to 4a. Now from this equation we can write y by 2 is equal to dy by dx is equal to a. Now substitute these two equations in the equation number 1. We will get y square is equal to 2y dy by dx into x plus y by 2 dy by dx. Now on rearranging this equation we will get y square is equal to 2xy dy by dx plus y square dy by dx the whole square. Now again rearranging, we will get y square dy by dx the whole square plus 2xy dy by dx minus y square is equal to 0. Here I just opened the brackets, that's all. Okay, so this is our required solution. Next, obtain the differential equation associated with the primitive ax square plus by square is equal to 1. Primitive means it is a general solution. Here the first equation is ax square plus by square is equal to 1, which is a given equation. So that is a general solution here. Now differentiate this equation. Differentiate this equation with respect to x. We will get 2ax plus 2by dy by dx is equal to 0. Now taking this 2 out common, and we will get ax plus by dy by dx is equal to 0. This is the equation number 2. Then multiplying equation 2 with x on both sides, we will get ax square plus bxy dy by dx is equal to 0. Now this ax square from equation 1 we can write it as 1 minus by square. So I wrote it like that, plus bxy dy by dx is equal to 0. Now bring this 1 to the RHS, we will get by square minus bxy dy by dx is equal to 1. Now bring this b to the RHS, we will get y square minus xy dy by dx is equal to 1 by b. This is the third equation. Now differentiate this equation with respect to x. See how many arbitrary constants are there, that much time we have to differentiate. So differentiate this equation with respect to x, we will get 2y dy by dx minus y dy by dx minus x dy by dx the whole x dy by dx square minus xy d square y by dx square is equal to 0. Now just multiplying with minus 1, we will get xy d square y by dx square plus x dy by dx whole square plus y dy by dx minus 2y dy by dx is equal to 0. This is the fourth equation. Here we had two arbitrary constants, a and b. So we have to differentiate, two times. Next, the fifth question is, find the differential equation corresponding to y is equal to a e raised to 3x plus b e raised to x. Here we have two arbitrary constants, so we have to differentiate twice. Now y is this is the first equation. Now differentiate this equation with respect to x. Our question was to find the differential equation corresponding to this solution. So first we have to differentiate it with respect to x. We will get 3a e raised to 3x plus b e raised to x. This is our second equation. Now subtract this first equation from this second equation. We will get y dash minus y is equal to 2a e raised to 3x. Okay. Now differentiate equation 3 with respect to x. This equation with respect to x. We will get y double dash minus y dash is equal to 3 into 2a into e raised to 3x. So I wrote it like this. This is just the same thing. Okay. Now this is our equation 4. Then from equation 3 we can write this 2a e raised to 3x as y dash minus y. Okay. So substituting that, we'll get y double dash minus y dash is equal to 3 times, here there is a 3 outside, 3 times y dash minus y. Now opening the brackets, y double dash minus y dash is equal to 3y dash minus 3y, and rearranging them you will get y double dash is equal to minus 4y dash. Here there is 1 minus y dash, and when this 3y dash goes to the LHS, you will get minus 4y dash plus 3y. This minus 3y goes to the LHS, plus 3y is equal to 0. This is our equation number 5, and this is the required differential equation. Now, by this is a sixth question. By the elimination of constants a and b, find the differential equation of which y is equal to e raised to x times a cos x plus b sin x is a solution. So this is our equation number 1. Here there are two arbitrary constants a and b, so we have to differentiate twice. So differentiate this first equation with respect to x, we will get y dash is equal to e raised to x minus a sin x plus b cos x using the product rule. Then then the next term should be like we have to keep this a cos x plus b sin x as such and differentiate e raised to x. On differentiating e raised to x, we will get e raised to x itself as the answer. So y dash is equal to e raised to x minus a sin x plus b cos x plus e raised to x a cos x plus b sin x. So this term is actually y itself. So rewriting this term as y in the next step, we will get y dash is equal to e raised to x times minus a sin x plus b cos x plus y. This is our second equation. Now one more time we have to differentiate. So we will get with respect to x, y double dash is equal to e raised to x minus a cos x minus b sin x. Okay, now keep this term as such and differentiate e raised to x. We'll get plus e raised to x times minus a sin x plus b cos x. Now on differentiating this y, we'll get y dash. So this is our next equation, and from equation 2, from this equation we can write y dash minus y is equal to e raised to x minus a sin x plus b cos x. Just substituting this, substituting for e raised to x times a minus a sin x plus b cos x. Okay, and putting that value here. So we will get this equation as y double dash minus y plus y dash minus y from this equation, y dash minus y plus y dash. Here one y dash is here. So on rearranging this, we can write it as y double dash minus 2y dash plus 2y is equal to 0. This is our required differential equation. Now the seventh question is, find the differential equation whose solution is y is equal to a cos of x plus 3. Now this is our equation number 1. Here there is only one arbitrary constant, and differentiate with respect to x, this equation number 1. Okay, so we will get y dash is equal to a times, when you differentiate this cosine, we will get minus sine of x plus 3, and when you differentiate the terms inside this parenthesis, you will get it as 1 itself. So the y dash is equal to minus a sine of x plus 3. Now divide the second equation by first equation. We will get it as y dash minus y is equal to minus a sine of x plus 3 divided by a cos of x plus 3, which is minus tan of x plus 3. So we can rewrite this equation as y dash is equal to minus y tan of x plus 3. This is the required differential equation in this question. Now the eighth question is, show that the set of function x 1 by x forms a basis. Basis means the solution of the differential equation x square y double dash plus xy dash minus y is equal to 0, and obtain a particular solution when y of 1 is equal to 1 and y dash of 1 is equal to 2. So first we have to check whether this set is actually the solution of this differential equation. So let's assume this is a solution of this given differential equation, and we can write the general solution as y is equal to c1x plus c2 divided by x, c1 times x plus c2 divided by 1 by x. Okay, if this is a property of differential equations, if these two are the solutions, then their sum is also the solution. Like we can write it like this: one arbitrary constant times the first solution plus the next arbitrary constant times the next solution. Okay, now there are two arbitrary constants. We have to differentiate this equation twice. Okay, this was our first equation: x square y double dash plus xy dash minus y is equal to 0. We have to differentiate it twice. We have to find the y dash and y double dash, then substitute in this equation number 1. If we get the answer as 0, then we can prove that this is the given set is actually forms the basis of this differential equation. Now on finding y dash, y was actually c1x plus c2 divided by x. So when you find the y dash, it is c1 minus 1 by x square times c2. This is the y dash, c1 minus c2 by x square. Okay, and differentiating this equation again, we will get y double dash is equal to, the c1 will go, and minus c2 times minus 2 by x raised to 3. This is actually x raised to 3. Okay, which is equal to 2c2 divided by x cube. Now putting these two equations in the first equation. Okay, and when you substitute these two equations in the first equation, you will get the answer as 0. See, first we have to multiply x square. First term in the equation number 1 was x square y double dash. So first we have to multiply x square with this y double dash. X square 2c2 x square 2c2 by x cube plus next term in the first equation was xy dash. So x times y dash, c1 x into c1 minus x into c2 by x square. Then there is a minus y term in the first equation, so substitute for minus y also. This was our y. So when you do all the calculations, you will get the answer as 0. So since the answer is 0, the set x 1 by x is actually, it forms the basis of the given differential equation. Next we have to find the particular solution. So to find the particular solution, first we have to find the values of c1 and c2. So first condition is y of 1 is equal to 1. Our y was actually c1 x plus c2 divided by x. Now substitute this 1, x is equal to 1. So we will get it as c1 plus c2. And the RHS is already given as 1. So c1 plus c2 is equal to 1. This is our equation number 3. Then y dash, then the next condition given is y dash of 1 is equal to 2. Our y dash is equal to c1 minus c2 by x square. Substitute for x is equal to 1. You will get y dash of 1 is equal to c1 minus c2 divided by 1 square, which is equal to 2. It is already given. This is our fourth equation. Now add these two equations. We will get 2c1 is equal to 3. So from that we can write c1 is equal to 3 by 2. Now substituting for c1 in equation number 3. So and from that we can find the value of c2, and it turns out to be C2 is equal to minus 1 by 2. Okay, C2 is equal to minus 1 by 2. So our particular solution is y is equal to C1x plus C2 divided by x. This was our general solution. Our particular solution is y is equal to 3 by 2x minus 1 by 2x. This is our particular solution. This is our answer. Thank you.